Starting with presentation 5, Sao Paulo, Brazil, team 1. It's a mission 13 flight experiment.
So, good morning everyone, and first of all, thank you for the opportunity of being here.
We are Ricardo Sensi, Roberto de Bortoli, Renata Miller, Isabella Batistella, and our mentors are Victor Bernardes, Andrea Weber, and Daniel Egg. We study information technology at the Technical High School Instituto Federal de Santa Catarina, which is located in the southern state of Santa Catarina, a region outside the technological pole of the country.
The Instituto Federal is a public educational institution present in all Brazilian states, which offers professional and technological education, with emphasis in the development of regional economies. The Brazilian clay filter is considered the best water filter in the world, according to the Drinking Water Book, being able to filter even sewage. It's composed by 2 compartments separated by a candle, which contains activated charcoal in its composition. Activated charcoal is a substance with great absorption power that's responsible for the water filtration. What boosts the water through the candle is gravity.
So, this research was encouraged by the future long-distance space travel and colonization plannings. These events will need water reuse because it is unpracticable landing supply missions for the sake of the exorbitant distances. Considering that, our objective is to test the water filtration process using activated charcoal in microgravity. But how would we do that? Here on Earth, under gravity effects, it's broadly known that a fluid located in a compartment A above a compartment B tends naturally to dislocate to the extremity B if nothing is stopping its passing. However, in microgravity, there's no definition of what's above and what's under. So how would the liquid be transported to the extremity B? We found this answer on capillarity.
And what is capillarity? Capillarity is the tendency fluids present to move up or down in capillary tubes or to flow through porous bodies, yet against gravity caused by superficial tension. When a fluid contacts a solid surface, it is submitted to 2 different forces, the cohesion and accession. The union of these 2 forces results in capillarity phenomenon. As an example, we can think about water from plants, which goes up from the roots to the leaves.
Considering it, our experiment is divided into 2 compartments. One of them contains a layer of activated charcoal and cotton, and the other is filled with a solution of methylene blue. This substance was chosen because of its coloration and affinity with the activated charcoal. Still, there will be a respiratory tube to exchange air between the volumes, in order to equalize the FME pressure.
And how will it work? After opening the clamp, the FME will be lightly shaked to ensure that the solution contacts the activated charcoal. The idea is that when it gets in contact with the activated charcoal, the solution will be filtered through capillarity and then retained in the cotton. As activated charcoal has very high porosity, we expect that capillarity will be able to replace gravity in the filtration process. And the advantage of using activated charcoal in the filtration process is that even if it's not completely removed from water, it does not present any risk to human health.
The group assembled 2 FMEs. One of them, the control experiment, will be maintained and supervised on laboratory on Earth, and the other, the fly experiment, will be sent to ISS for microgravity. The experiments will have their clamps opened and closed simultaneously for further analysis.
After the experiment is finished, we will compare the liquid filter in microgravity with the one that was filtered under the action of terrestrial gravity. In addition to analyzing whether the filtration occurred, we will analyze its efficiency in relation to the Earth by comparing the concentration of solutions.
This comparison will be made by a spectrophotometry using a light beam of wavelength 665 nanometers, which will be inserted into the samples. By means of this technique, we will be able to measure the absorbance of the samples, which is the amount of light the sample can absorb. The higher the absorbance, the higher the concentration. This will let us know if there is any difference between the two samples concentration.
We thank our teachers, Andrea Weber, Daniel Eco, and Victor Bernardes, Garantia team, Lucas Fonseca and Patricia Braco, and all the financial supporters.
And stand and get ready. But before we take questions, I just wanted to say to your team that this is a very exciting experiment, and it's so interesting that it happened to follow Jeff Manber's presentation, because exactly what you guys are attempting here speaks to what he was saying about how students can support the return to Moon and possibly staying long-term there. So that's a really exciting correlation between the two. Do we have any questions? No? Okay, thank you guys so much.
Hi guys, I'm Lena. I'm from the University of Maryland. My question is, do you know if there are any water filtration systems that are already being used in space?
Yes, there is. Actually, currently we are using iodine to filter, but there is a disadvantage because if iodine is not completely removed from water, it can be toxic, it can harm human health, so our would be better.
Thanks, awesome job.
Okay, thank you. Thank you.